Okay, so let me see. Yes, what I would like to discuss today, and it will probably take the full lecture, is one kind of bond that we discussed last time, and this is the covalent bond. I'm going to discuss this particular type of bond because it gives us a feeling of, in general, about other kinds of chemical bonds, and also because you really see how quantum mechanics in action can give you a prediction about why two atoms like to bind to one another, okay? Not just from a classical point of view, but from a real quantum mechanical point of view. The other reason I like to emphasize this type of bond is because the theory that we will be developing is going to be easily extendable to an extended infinite system. Okay, so we will use the same theory to extend our discussion to an infinite system. Okay, but we will start with a system made of two atoms, and we're going to discuss how two atoms interact with one another and form a chemical bond and bind to each other. All right, so the problem is consists in the following. We have a nucleus here, and we have a nucleus here. And let's, for simplicity, consider two hydrogen atoms, HH. All right, so this is just a proton. This is just a proton. So what we're going to discuss is covalent bond in the H2 molecule for practical purposes. Okay, just because it's the simplest covalent bond we can think of, right? It's only one proton, actually two protons, one here and one here, and of course two electrons, because each hydrogen atom brings two electrons to the problem. Now, if the two protons were very far apart, let's say one here and one here, we know the solution of the problem, right? There will be an electronic cloud here, a 1s state. So the electron will be in the 1s state of the hydrogen atom. The other electron will be here in the 1s state of the hydrogen atom. And they probably will not see each other. They would not see each other. They would just live independently as far as, they are sufficiently far apart. But now the trick is, we're trying to bring them closer to one another, and we want to study the situation in which the two are close enough that they form a chemical bond. All right? So we have one electron coming from this atom and one electron coming from the other atom. But we know for quantum mechanics that electrons are not distinguishable particles. So we cannot say any longer that an electron is coming from this and an electron is coming from that. What we know in practice is that we have two electrons somewhere localized, somewhere around these two protons. These two protons will give rise to an attraction, right? There will be a well that attracts the electrons close to the two nuclei, and of course the potential. So what I'm drawing here is some isosurface lines of the potential. So these two nuclei will generate two Coulomb potentials centered here and here. So these lines here are the isosurfaces of the potential, of the Coulomb potential, due to the nuclei, to the two protons. And the two electrons will be located somewhere here and will respond to the quantum mechanically to the presence of this potential determined by the two protons. So from now on, we will not distinguish whether the electrons were coming from one or from the other. We're just dealing with two electrons. Two electrons living in this complex, with this potential with a complex shape. There's one thing I'm forgetting when I'm saying this, and this is the interaction between one electron and the other one. For the purpose of this discussion, let me assume that I can forget about that. Otherwise, the discussion becomes too complicated. So we're going to completely forget electron-electron interactions here. Interactions. Let me put a cross on top of that. Not because they don't exist, but because that would make my theory very complicated. And as we discussed yesterday, as soon as we move into the many-body problem in quantum mechanics, the discussion becomes very complicated. So I'm not saying that, I'm not claiming that it's not there. I'm just claiming that our discussion will give qualitatively the same results if we neglect the electron-electron interaction, and it makes our life much, much simpler if we neglect it. All right, so now let me take a cut here and draw the potential, for example, along this cut here. Okay, so I'm going to take a line there, and I'm going to express my potential along this line here, and I call it, I can call it R. It's just a line, I mean a straight line going through the centers of the protons. I'm just because I want to draw the potential, and the potential will be the sum of two Coulomb potentials. So it will look something like that. Actually, okay. So this is, if say this is the origin, this will be the potential seen by each electron. Each electron in this system will see a potential, at least if I look at it along this line, this is the potential that will be seen by the electron. It's a two-well potential. Proton here and the proton here. So we need to solve the quantum mechanics of an electron in this potential. Of course, in 3 dimensions. Here I'm just showing a cut of the potential. We have to do it in 3 dimensions, of course. The solution to this problem will give us the charge density, the wave functions, and the solution to the H2 problem. Now, I guess you're familiar with part of this problem, right? You're certainly familiar with the solution of this problem if this was not there. Suppose I bring this proton very far apart, right? Then this potential will be just a Coulomb potential here, and then a Coulomb potential somewhere else. I mean, very far apart from the... so it will be essentially the sum of 2 independent Coulomb potentials. And we know the solution to that problem. We know the solution of the problem of a simple Coulomb potential. In fact, it's just a proton, so the solution is just the hydrogen atom solution. The problem, of course, that these two are now close to one another. So how can we use the information that we have that we can extract from the solution of the hydrogen problem in order to solve this more complicated problem? Okay, let me write the full potential, which is the sum of these two potentials, as actually a sum of two potentials, right? So let me now here plot this one and this one. By this, of course, I mean by these two lines. Let me call this V1. V1 is the Coulomb potential due to this proton. And these two lines are V2, the Coulomb potential due to this proton. Right? And therefore, V of R, V1 of R plus V2 of R. Right? I'm just expressing the total potential as a sum of the two Coulomb potentials coming from the two atoms, from the two hydrogen atoms. Any question about this? Is it clear? Right? That's exactly, I mean, we have two protons, so we have two Coulomb potentials. So this is the Coulomb potential due to atom 1, and this is the Coulomb potential due to atom 2. I don't want to write it explicitly as E square over R and so on and so forth, because this discussion is actually more general than the hydrogen atom discussion. Here can be any atom. It can be any potential due to the presence of an atom here. So I want to keep the discussion more general, but if you like to think in practical terms, you can think of it as the Coulomb potential due to the proton. If you want to visualize it, if you want to think in practical terms. If we deal with H2, of course, this is in practice the Coulomb potential due to that. But let me be more general. I mean, this is in general the potential felt by an electron sitting on atom 1, and this is the potential felt by an electron sitting on atom 2. If, of course, atom 1 didn't exist, and vice versa. This is the potential that the electron would feel if this one was there, but this one was removed, of course. The total potential is the sum of the two, obviously. So an electron living in this world will respond to an Hamiltonian, which is given by the sum of the two potentials, right? So we need to solve this problem. The solution to this problem will give us the wave functions and the energies for our problem, for our combined problem. And let me remark once again that this one, this part here, would be the Hamiltonian for atom 1, right? Vice versa, if I take this plus this, this would be the Hamiltonian of atom 2. So this is, I can call it H1, and this I can call it H2. In other words, if I solve Hamiltonian H1, I would get the solution for atom 1. If I solve Hamiltonian H2, I would get the solutions for atom 2. What I need to solve is something which is a combination of the two. Not the sum of the two, by the way. The potentials sum up, but the Hamiltonians don't sum up because I have the kinetic energy in both sides. Certainly what I can say is that, well, if I'm good in atomic physics, I know the solutions of H1, right? Suppose that I mean, my knowledge of atomic physics is infinite. I mean, I know everything about atomic physics. And so I know that H1 has some solution. For example, the 1s solutions of the hydrogen atom. So if this is the Coulomb potential due to a proton, E square over R, then I know that the solution, I mean, at least the ground state solution of H1 is the 1s state, centered here. Okay, so in other words, I know that there will be here a level, which is the 1s level, minus 13 point something below the vacuum. And there will be a wave function here, the 1s wave function, which is a solution of V1. This is what I'm expressing here, right? Similarly, of course, I know that if I sit on H2, this also is a trivial problem, or at least something that I can assume I can solve. This will be, again, a 1s state. Mind you, I'm not putting here explicitly the dependence on the position, but clearly this is the 1s state centered here, and this is a 1s state centered here, right? So it's a different 1s state. It's not the same one. But the energy is the same. Shall I call it, let me do this, sorry. Let me put the 1s here and put 1 here. So this is 2. Okay. By this, what I mean is this is the 1s state centered at position 1, and this is the 1s state centered at position 2. So this is 1s 1, and here I have E1s. It's the same orbital, simply centered in a different position. How can I use this information, which I assume I know, right? In the case of the hydrogen atom, it's trivial. In the case of more complex atoms, I assume that I've been able to calculate it or to determine it in some way. How can I now use this information to solve this problem, which is my problem? My problem is to solve the quantum mechanics of an electron in the potential given by the sum of the two potentials, V1 and V2. Now, in order to solve this problem, I need to make some approximations. I mean, in principle, I could solve it exactly given some, I mean, if I was really trying to, I mean, I could solve it, I mean, as a second-order differential equation, numerically or not analytically, certainly, but numerically. But let me suggest an approximation that will allow us to understand a number of things about this Hamiltonian. So let me suggest that when I look for the solutions of Hamiltonian H, that is wave functions phi such that this is an eigenstate of H, H being the full Hamiltonian, the one given by V1 and V2, I look for solutions where phi is a linear combination of these two orbitals, these two wave functions. Plus A2 phi 2 1s. Of course, I'm restricting myself, the set of possible solutions considerably. But let me assume that I can do it, that I can express my solution as a linear combination of the solutions to the two different problems. It's certainly not going to be an exact solution. It's an approximation. So I'm introducing an approximation. Because, but we can tell that this approximation is certainly good in the limit where the two protons are very far apart, right? Because if they are very far apart, we know that the solution is either this or this. So trivially, by having A1 equals to 1 and A2 equals to 0, or vice versa, I can recover the solution in the limit where this is very distant, where the two protons are very distant. So in some sense, what I'm doing is I'm saying, well, suppose I start from a solution I know, that is that the two wave functions are independent, and let me bring the two protons closer and closer and closer. The true solution will become a mixture of the original solutions of the two independent problems. So qualitatively, this is the argument that I'm using to justify my choice of the wave function expressed in this form. Again, it's not an exact statement, but it is an approximation. So let's see the consequences of expressing the wave function in this way. And let's see if we can find a way to determine A1 and A2, right? Our unknowns at this point, if we want to solve this problem, are A1 and A2. Of course, the other unknown is the energy. Phi 1, 1s, phi 2, 1s are given. They are the solution of the atomic problem, which I'm assuming I've already solved. Okay? And similarly, I assume that I already know this energy, which in the case of the hydrogen atom is the 1s energy of the hydrogen atom. Okay, so let me try to solve this problem by explicitly using this expression for phi. So H is written there. Plus V1 plus V2 phi. Let me drop the 1s index for simplicity, okay? So I'm going to drop the 1s just for clarity. So this is the equation I would need to solve for A1, A2, and E, my three unknowns. All the rest is fixed and is given. Let me now notice something interesting here on the left-hand side. Again, this is H1. And I know that phi 1 is an eigenstate of H1. So when I apply this expression to the first term, let me do H1 plus V2 times phi 1. Okay, so let me write this as A1 H1 phi 1 plus A1 V2 phi 1. Right? What I'm doing is I'm applying the left-hand side of the product to the first term on the right-hand side. But in doing that, I'm writing the Hamiltonian as H1 plus V2. Right? That's my definition. Let me now apply, again, the left-hand side to the second part of the product, phi 2. If I do that, however, I decompose this in a different way. I'm going to now write it as H2 plus V1. It's equally good, right? V1 phi 2. Okay? It's clear why I did it. I did it because H2 phi 2, I know the solution already. Similarly, H1 phi 1, it's the solution of my atomic problem. Right? So I've extracted out of my H the part for which I know the solution of. And I left V2 and V1 here as an extra term. H1 phi 1 is the atomic energy for state phi 1. So this is A1 E 1s. Let me actually, instead of calling it 1s, let me call it E naught. I mean, this is the atomic energy, okay? I'm using 1s because I was assuming that this was an hydrogen atom, but I don't want to restrict my discussion to the hydrogen atom. If you prefer, you can assume that E naught is the hydrogen atom energy if this is a proton and you have only one electron. But I want to be more general. The point is that this is the atomic energy. It's the eigenvalue of my atomic problem for this atomic wave function. And someone has given it to me. I assume that that problem has been already solved, the atomic problem. So this is, if you wish, E1s. If you wish to be more general, it's the atomic energy of state, of the atomic state phi 1 times phi 1 plus A1 V2 phi 1 plus A2, same with H2 phi 2. H2 phi 2 is the solution, it's the atomic problem. So this will be same energy, whatever that is, 1s, 2s, whatever, same energy times phi 2. This is, of course, only the left-hand side. There's always a right-hand side, which I can continue writing. Okay. So again, this is an equation of which I need to find A1, A2, and E, my three unknowns. All the rest is given. However, it is an equation between functions. It's not an equation between numbers. In fact, if I want to determine three numbers, I would need three equations between numbers, right? At least. Here I have a single equation, but it is an equation between functions. So in fact, I have somehow infinitely many equations between numbers that I can derive from an equation between functions, right? If I have an equation between functions, for example, I can say that these two functions, the left-hand side and the right-hand side, have to be equal in all the points, right? So this is, in principle, gives me an infinitely large set of equations between numbers. And here I have only three numbers. So in some sense, I'm over-complete in my in the number of constraints that I'm putting to this equation. But let me try, instead of looking at, say, the equality at a given point, which will give me an equation between numbers, let me do something else. Let me try and extract out of this equation between functions two equations between numbers. And the way I do it is the following. I take left-hand side and right-hand side considered as functions, and I project them onto phi 1 first time and phi 2 second time. What do I mean by projection of a function onto another function? Are you familiar with this concept or not, of a projection? The projection in mathematical terms essentially means that, I think I can write here. If I have a function there on the left-hand side, suppose I have a function here, f, and I want to project it onto another function, say phi 1, for example, what I mean is the integral over the whole space of f times phi 1, right? That's the projection. In fact, you might think of this in bracket notation. I'm sure you've seen bracket notation, right? So what I mean by that, by projection, is simply, I simply don't want to, I don't like to write it in terms of brackets. Otherwise, I would express the, if you liked, I mean, I could express this as a bra, and I would projection onto phi 1 means that I'm taking this and I'm projecting it onto phi 1 or phi 2. If you don't like brackets, the projection means that I'm essentially taking a function and I'm taking the integral times the function that I want to project the other function onto. Okay? So that transforms a function into a number, right? Because this is an integral, so this is a number. So either you see it as a bracket projection, or you see it just as an integral times a function, which I can choose. In fact, my previous argument that I could have chosen to equate these two functions at a given point in space, which was again another way to extract out of an equation between functions an equation between numbers, would correspond to project my function onto the delta function. If if phi 1 is the delta function at a given point, right, this integral gives me the value of the function at that point. So it's the same essentially. I'm simply using a different, when I say that I equate two functions at a given point, it's equivalent to saying that I'm projecting that function onto the delta function centered at that point. Here I don't like delta functions, so I'm going to project it, for example, onto phi 1 and onto phi 2, separately, of course. So I'm going to take this equation here, left-hand side and right-hand side, and I'm going to project it onto phi 1 first. How familiar are you with bracket notation? Are you all familiar with that? Can I work with bracket? Because that would simplify my notation if I do that. Okay, great. So then let me use bracket notation, because it's otherwise I would have to write everything in terms of integrals, which is okay, but it's a bit complicated. So this is my bra part of the function, and what I'm going to do now is I'm going to project it onto phi 1, both sides. And I'm going to write the result here in the next line. So, first term, phi 1, phi 1. A1, E0, phi 1, phi 1. But what is phi 1, phi 1? 1, right? Because it's phi 1 is the solution of an Hamiltonian. So this must be normalized. So this is 1. Plus A1. In fact, here I have to be careful. The wave function is actually to the left here. When I write it in bracket notation, this has to be phi 1 v2. And even here, sorry. If I write it in bracket notation, it has to be phi 2 v1, like this. Okay, because I have to project it on the left side when I write the Hamiltonian here. So this is phi 1 v2 phi 1 plus E2 A2 E0 phi 2 phi 1 plus A2 phi 2 V1 phi 1. And that's the left-hand side. What about the right-hand side? EA1 phi 1 phi 1 plus EA2 phi 1, sorry, phi 2 phi 1. This is again 1. What can I say about the other terms? For example, this one, phi 2 phi 1, phi 2 phi 1. Why? Why? Why is it orthogonal?
Okay, they are the eigenfunctions, the eigenvalues for the Hamiltonian H.
Phi 1 and phi 2, are they eigenfunctions of H?
No, H1 and H2. But if we
Right, so
require
phi 1 and phi 2 are eigenfunctions phi 1 of H1 and phi 2 of H2. Is there any reason why they should be orthogonal? No. There are two eigenfunctions of two different Hamiltonians. No reason why they should be orthogonal. Of course, H1 is, this is orthonormal, so this is 1. But phi 1, phi 2, they're not, they're eigenfunctions of two different, actually they have the same shape, in fact. They don't have nodes in between. How can you make them orthogonal? No. However, in the spirit of our original approximation, where we stated that we wrote our wave function as a linear combination of two orbitals phi 1 and phi 2, because what we had in mind was a system in which we were just perturbing the solution given by the two independent systems, we can assume that these two wave functions are sufficiently far from one another. If they get too close, this original approximation is going to fail, to break down, because we've realized that this is going to work in the limit where the two wave functions are very far apart, but when they get very close, their overlap between these two wave functions is going to be substantial, and therefore there's no guarantee that the wave function can be still expressed as a linear combination of the original wave functions, which are wave functions that are valid as long as the two Coulomb potentials are very far apart. In some sense, perturbation theory, which was our initial argument to justify this choice, if the two wave functions get too close, is going to break down. All right? So, although these are two wave functions for two different Hamiltonians, we can.
Please.
Yes.
I want to know, the both functions are in the same spaces.
Yes, in the real R3.
I think maybe the same. If each function is acting if phi1 is acting there and phi2 here, when you will take the bracket with the
Right, it's exactly my argument. If these are sufficiently far apart, okay, the overlap between phi 1 and phi 2 is going to be small. Certainly not 0, it's going to be small, exponentially small, because these are exponential functions. So if I continue to keep this approximation, I need to assume that these two wave functions are far, are not too close, because otherwise there's no way I can write phi as a linear combination of the two independent solutions, and then just using perturbation theory. The argument is mathematically a bit more complex than that, but allow me to, for simplicity, to say that, okay, let me approximate this to 0. So I'm going now to make sure that we understand where are the approximations here. Yes, I'm coming to a second. So this is one, and I'm highlighting with red the approximations. This is an approximation. And the second approximation is that phi 1, phi 2 is equal to 0, okay, which is an approximation. Yes?
Okay, if we see minus the norm of the length from the origin line.
Yes.
So whether they are close enough or whether they are far.
Yes.
If we sum up on the whole space, then the wave functions vanish rapidly at those inputs. So the inner product, the projection will be zero, right?
The projection would be proportional to the overlap between the two wave functions, right? So if these two wave functions were to sit on the same place, this would be 1, right? If I bring this proton here, phi 1 and phi 2 will be exactly overlapping, and so this will be exactly 1. They're actually the same wave function. So this product here, this overlap, is proportional to the overlap between these two wave functions. And if these are sufficiently far apart compared to the decay length of the exponential wave function, then I can claim that this is at least small for our purposes. Okay? But the important thing to keep in mind that it's 0 not because they're orthogonal, but because of physical reasons. Yes?
We are considering these two atoms to come to form a bond.
Yes.
So why do you have to consider an approximation to one bond?
Okay, that's a very good question. Our goal is to see the formation of a bond. How can we continue assuming that the two wave functions are very far apart? Because the theory of formation of chemical bond in the limit where these two wave functions have a large overlap is much more complicated than that. Okay? So I need to approach the problem with some reasonable approximations that allow me to develop some mathematics out of it. The truth is actually probably closer to my approximation than to your statement. In other words, the two wave, even if you take the hydrogen atom, the overlap between the two 1s orbitals in the real system, when you bring them together, is not that big. It's not that big. Consider that in the hydrogen atom, the distance between two, in the real system, this distance for the H2, molecule, for example, is about 1.4 Bohr radii. Okay? And the decay length of this is a Bohr radius. Okay, so yeah. So by the time you get to this point, this wave function has become 1 over E, and this has become 1 over E here. So the overlap is there, but it's not really heavy. It's not substantial. Okay? It's not going to change quantitatively. It's not going to change qualitatively the result. It's going to change quantitatively the result, but not qualitatively. Okay? But you're right. I mean, of course, if we want to see the formation of the bond, we need to have these two wave functions overlap. So how can we approximate now that the overlap is 0? We are treating the problem from a perturbative point of view. So we have to approach and assume that the two remain at some distance. But we will see that there are consequences that are qualitatively consistent with the formation of a chemical bond anyway, if you proceed with this. Okay, so we're going to remove this. We're going to remove also this one as a consequence. And, well, the other thing we can notice is this. This is what? Wait a sec. This is phi 1v2. No, that's fine. That's fine. Sorry? A1. Oh, this one is A1, right? No, A2. This one is A1. No, A2, this one. Sorry, thank you. Thank you. Okay. Now, let me now here repeat the same exercise. So this was projected on phi 1. And now let me do the same thing by projecting onto phi 2. Okay, the same equation, but now projected onto phi 2. Well, now we can do it quickly, right? The first term, if I project it on phi 2, is, within our approximations, of course, 0, right? So this is not there. I have to start with the second one. Phi 1, sorry, A1 phi 1 v2 phi 2. That's this. Here, phi 2 is 1. So this is just A2 E naught. This one, well, remains more or less what we phi 2. And then we have the right-hand side. This one disappears, and this is just EA2, because phi 2 is 1. Write now this one here, otherwise I'm phi is equal to A1 phi 1 plus A2 phi 2. Because I'd like to I want to work on the left side of the blackboard here. All right, so I have two equations, and these two equations now are equations between numbers finally. It's only two, by the way, it's not three. And I have three unknowns. However, let me rewrite, just mathematics now, this set of, this pair of equations. These are actually linear equations in my unknowns, right? A1, A2, and E appear both here and here in a linear fashion. So let me write them in matrix form. I'll first write it as a matrix, and then you'll recognize that I'm writing exactly the same thing. So let me write it like this. Here. Sorry. Where's the other A1? Here. Plus phi 1 V2 phi 1. Then here I have phi 2 V1 phi 2 phi 1. Sorry. Here phi 1. Oops. V2 phi 2. And here I have E naught plus phi 2 V1 phi 2. Yes?
I don't understand how we get okay, E add to you said on, yes.
This one?
Yeah.
Okay. This was the projection of the right-hand side onto phi 2. Right? Yeah, I mean, the bottom line is the projection on phi 1. The top line here, you see, phi 1 here and phi 2 here. I'm projecting this equation between functions twice. First on phi 1, second time on phi 2. So these are my two equations, up below and above the original equation, okay? So now actually this one is projected on phi 2, of course. So then phi 2, if I project this one on phi 2, this is 1 and this is 0, right? The 2. So this becomes EA2. So I have a central equation between functions. Below this central equation, I'm projecting on phi 1. Above this equation, I'm projecting on phi 2. And now I'm considering the two equations between numbers below and above the original one. And what I've done is I've rewritten these two equations in matrix form. You just have to recognize that I've done a good job. Actually, can you check that I've done a good job? Right, so this would be the first one, right? So it's A1 times E naught plus phi 1 V2 phi 1. Where is A1? A1 is here, E naught, A1, phi 1 V2, phi 1. Okay. Then I have plus A2 times phi 2 V1 phi 2, phi 1. Here you go, phi 2 V1 phi 1 equals to EA1, EA1. Okay? You can check that the first one is also correct. All right? I've simply rewritten these two linear equations in matrix form. And I guess you now recognize this equation, or at least the form of this equation. This is an eigenvalue problem for E1. A1 and A2 are my unknowns, in addition to E, of course. Obviously, A1 and A2 obey a special relationship. The sum of their squares must be 1. Why is that so? Well, I just obtain it from here. I want to impose that phi is normalized, right? But when I do phi is equal to A1 squared plus A2 squared, because all the cross products give me 0 in this approximation. The approximation of phi 1 projected on phi 2 is 0. All right? So A1 squared plus A2 squared must be 1 if I use this approximation. Well, I'm not using complex numbers. I'm using real numbers. A1 for me is a real number. It's a one-dimensional. I don't need to invoke complex numbers here. I can work with real numbers. All right. So I have a standard 2x2 quantum mechanics, diagonalization of a matrix, right? And A1 and A2 are going to be my eigenstates, or at least the coefficients that express my wave functions in that basis, and E is going to be my energy. Let me simplify the notation a bit further. What can I say about these two terms, this one and this one? Let's think about it seriously, carefully. Phi 1 is this one here, okay, the orange one. V2 is the Coulomb potential on the other side. Phi 1 is again my wave function on the initial side. Okay. Let's look at this one now. Phi 2 appears twice, and it's here. And V1 is the potential on the other side. What can I say about these two terms? The functions here are just inverted, right? But if the problem is symmetric, if this atom is the same as this, the integral, that is the expectation value, must be the same. And because it appears in this term here with E naught, let me call it delta E naught. I'm just giving it a name, right? I'm just call it in order to simplify bit notation. So by delta E naught, I mean this object. The product between the square of the wave function at the given site times the Coulomb potential at another site. And I call it delta E naught. What about this one and this one? Here it's a bit more complicated, but it's a wave function on 2 times wave function on 1, Coulomb potential on 1. Here, wave function on 1, Coulomb potential on 2, wave function on 2. They're just reverted, okay? When I take the integral, the two give me the same number. If, of course, the two atoms are the same. All right? This term here, I call it T. In solid-state physics, this is typically takes a name of hopping parameter. It's called hopping because you're jumping from one wave function to the other one. And there are some physical consequences that derive from this particular term. So just keep in mind that this is, in the jargon of solid-state physics, this term is called the hopping term, because it's hopping from one side to the other one with the help of a Coulomb potential. Similarly, delta E naught is typically called the on-site term, because it's something that depends on the wave function at the given site. So we have introduced two new entities, T, the hopping term, and the on-site energy. So we can now rewrite I'm just going to rewrite it for simplicity with a new notation. So it's going to be E naught plus delta E naught, T, E naught plus delta E naught, A1, A2, okay? So now it looks even simpler. This 2 by 2 matrix is of the form A, A, B, B. Very simple. Hermitian, same numbers in the diagonal. What are the eigenvalues of this matrix, 2 by 2 matrix? If I give you a matrix of this form, can you tell me, right on the spot, what are the eigenvalues of this matrix? Or do you need to calculate them? Okay. Any good physicist would tell you immediately what the eigenvalues of this. I mean, you're still at the learning stage, but be ready to learn it by heart, what the eigenvalues of this are. So let's calculate them, okay? We'll do it now, and that's the last time I'm going to do it at the blackboard. Next time, I assume you'll know it. Okay, secular equation, A minus lambda, right? Determinant of secular equation, A minus lambda square minus b squared equals to 0. A minus lambda equals to plus or minus b. Lambda equals to a plus or minus b. Okay? Minus plus, whatever. Okay, so this matrix AABB has these two eigenvalues. Actually, I need to be careful and put the absolute value, which doesn't change if this is a real number, because if the sign of b is negative, I can just change the two signs. It's irrelevant. But if this is a complex number, of course, I have to be careful. Well, if this is a complex number here, I would have b star, of course, not b. So I'm assuming that I'm working with so let me assume that I'm working with real numbers to keep this. Whatever. Let's do it like that. Okay. So this is probably the most common 2 by 2 problem, actually the most common quantum mechanical problem you can think of, a two-level system, a two-state model, and the eigenvalues are given. If these two numbers are degenerate, that is, if the two energies are the same, they're given by a plus or minus the off-diagonal term, absolute value. Okay? Keep it there somewhere in your brain, because this will be very recurrent in physics, if you want. Okay. Well, let's be a bit more careful than that. Let me be, well, okay, let me do this. Wait a second. Because I want to make sure we get the signs properly. So. So let me take, I want to get the signs properly, because I also want to get the eigen states. So let me take the solution A plus B. Lambda plus is equals to A plus B. Okay? Right, so the A1 plus B A2 equals to A plus B A1, right? And of course, B A1 plus A A2 is equal to A plus B A2. I'm just writing now the two linear equations, assuming that I'm looking for the eigenstates with eigenvalue A plus B. I know there are two solutions, so let me now find the values of A1 and A2 that satisfy the, that correspond to the eigenvalue A plus B. Okay, so here I have this one disappears, right? So I have that A1 has to be equal to A2. And obviously the same here, right? This disappears, and so A1 has to be equal to A2. So that's the same solution. Which means if I consider that the squares of the sum of the squares is 1, A1 equals to A2 means that they have to be 1 over square root 2, each one. But I mean, this is not really relevant for us. The important thing for us is that when I have the plus here, A1 must be equal to A2. That is, they are both going to be equal to 1 over square root 2 because of the normalization constraint. Vice versa, and let me now use the orange color. If I'm looking for the minus solution with the minus sign, what changes here is the minus sign here and the minus sign here. And what you see is that now A1 must be equal to minus A2. Both equations are satisfied only if A1 is equal to minus A2. Okay? So the one with the minus sign corresponds to A1 equals to minus A2. Good. That's important because now I'm going to use these findings to determine here the wave functions. In fact, I can say that there are two solutions, one which I call E plus, which is given by E naught plus delta E naught plus T, and the corresponding energy, in the corresponding wave function is the one with the plus, so it's 1 over square root 2 phi 1 plus phi 2. A1 is equal to A2. Are you okay? You're lost.
No, I'm okay.
Huh?
I'm okay.
You're okay. Okay. So, solution with plus. A plus is A plus B. A plus B. In that case, A1 is equal to A2 and are equal to 1 over square root 2. If A1 is equal to A2 and is equal to 1 over square root 2, the wave function will be 1 over square root 2 phi 1 plus phi 2. Here you go. Second solution, E minus E naught plus delta E naught minus T. Eigenfunction phi minus phi 1 minus phi 2. Okay? Yes?
This calculation is true for the square matrix or for n more than 2.
N by n matrices?
Okay. Let's
Oh, you want a 3 by 3, for example?
okay, maybe okay. If it's
And you want a 3 by 3 of the form what? A, and B, B's everywhere? No, it's complicated. No. I'm just talking about 2 by 2 here. I'm not assuming, although, I mean, you might remember what eigenvalues for a 3 by 3 matrix of this form could look like. I don't, in fact. I would have to think about it. 2 by 2 is straightforward. I mean, I would like you to remember it by heart, that the 2 by 2 Hamiltonian of this form, energy in the diagonal, off diagonal term, the eigenvalues are the diagonal term plus or minus the off diagonal term. Okay? That's something that is very recurrent in physics. Very, very. Both in particle physics, in solid state physics, in any other field, atomic physics, any field of physics. So this is what we're doing here. So out of this 2 by 2 problem, we have extracted two eigenvalues, E plus and E minus, given by A plus B, A minus B, and the corresponding eigenfunctions. Good. Oof. So let me now, for a moment, go back to my extreme case, where the two protons were very far apart. Let's see if I can recover the solution in the extreme case. If I've done everything properly, I should be able to recover the solution in the extreme case. Well, in the extreme case, if these two wave functions, these two protons are very far apart, I know that the solution is the 1s orbital here and the 1s orbital there. And in particular, I know that their energy is the 1s energy, the atomic energy, E naught. So what happens in the limit of in the limit where these two atoms are very far apart in my equation? Which term is going to be affected by the fact that I'm separating the atoms one from the other one? Well, E naught is certainly not going to be affected. E naught is an atomic property, so it's not going to change if I take the two atoms far apart. What about this term here? This is the overlap between the wave function at site 1 and the Coulomb potential at site 2. If I bring the two atoms far apart, this term will vanish. Same with this term, right? Here is the wave function at site 1 and wave function at site 2. The overlap will decay to 0 if the two atoms are very far apart. So both delta E naught and T will go to 0 if my two atoms go very far apart from one another. So let me actually do this here. If d, say d, the distance between the atoms, goes to infinity, then delta E naught goes to 0, and also T goes to 0. So my two eigenvalues, E plus and E minus, become E naught. That's exactly what I expected. E plus and E minus both become equal to E naught. I know that the energy must tend to the atomic energy if the two atoms are very far apart. There is a problem, however. I was expecting that in that limit, these two wave functions, the two solutions would be this wave function and this wave function. What do I get here? Linear combination of phi 1 plus phi 2, linear combination of phi 1 minus phi 2, regardless of the value of delta E naught and T. Whatever is delta E naught and T. If this becomes 0, it's still the same. Doesn't change. Why? So what is the problem? I got the right energies. I got what I wanted. The energies are okay. And what about the wave functions? Why do I get two wave functions which are not the wave function on atom 1 and the wave function on atom 2? Why do I still get a linear combination if the two atoms don't even know about each other?
Okay. If the energies E plus and E minus are the same,
Yes?
You have psi plus and psi ones, right?
Right? And then what can I do if E plus and E minus are the same? Then?
Superposition of the phi plus
Perfect.
psi ones.
Okay? So if the two eigenstates are degenerate, I can build any linear combination I want out of the eigenfunctions, right? So the fact that I get plus and minus here is just reminiscent of what I was doing before. But now that I know that the two energies are the same, and they are in the limit at delta E naught and t go to 0, I can just rearrange the eigenfunctions, building any linear combination I want. So I can take the sum and the difference, and I will get phi 1 and phi 2. Okay? That's the point. So you don't need to be surprised by the fact that these two wave functions are different with respect to what I expected. They are different just because it's a different linear combination of functions out of a twofold degenerate manifold. I have two degenerate states. I can build any linear combination I want out of eigenfunctions which are degenerate. And in particular, this is one of the many possible, the infinitely many possible linear combinations that I can build out of two degenerate, degenerate solutions. Okay, so nothing is wrong. Everything is right. It's perfectly legitimate, perfectly consistent. If delta E naught and t go to 0, I recover my atomic scenario, my atomic limit, within, of course, some additional considerations that I have to make about the wave functions. Good. So let me now imagine the process of taking these two atoms very far apart and bringing them closer and closer and closer. At the beginning, I will have the two wave functions, the two solutions, with some rearrangement, whatever, and these two energies. Let me just restrict my consideration now to energies for the time being. What's going to happen to the energies? Well, if I start bringing these two atoms close by, there are two consequences. First, there is a shift of the average position of these two energy levels given by delta E naught. In addition, there is a splitting between the two states, which is given by T. So delta E naught and T give rise to two completely different effects in terms of energy. One of them is just a rigid shift of both levels. Both levels used to be degenerate in the limit where the two atoms were infinitely distant. Now we bring them then closer to one another. This is a rigid shift, and this is a splitting. Let me discuss briefly the sign of these terms. What can I say about the sign of delta E naught and T? Well, not too much, in fact. It depends on what is the wave function here. Delta E naught, for example, is the product of phi 1, and V2. So it really depends what phi 1 and V2 are. But, well, product phi 1 is certainly a positive function. V2, what can I say about V2? Whether it's Coulomb, whatever it is an attractive potential, right? So this object is certainly negative. So what I can say, actually, is that delta, that's my white chalk. I can certainly say that delta E naught is negative, right? What about T? Here things get a bit more complicated because I know that V2 is negative. It's an attractive potential, so it must be negative. About phi 1 and phi 2, well, if they are 1s states, they are both positive, right? The 1s state is positive all over the space. So if they are 1s states, I can certainly say that this is negative. If 1s states. I cannot, say that this is a general statement, however. Think of, say, phi 2 being a p-wave function with a node. A p-wave function takes also negative values. So if the negative side of the wave function happens to be where overlapping with phi 1, which is perhaps a positive function, the whole thing will become positive. Okay? So I cannot really say too much about the sign of T in general. For 1s states, I can certainly say that T is negative. So for the hydrogen atom, I can certainly say that this is negative because 1s is positive. They're positive wave functions. Okay? So delta E naught is negative. T is, well, typically negative, but not necessarily. I bring the two atoms close to one another. So there will be, sorry. There will be a shift, a rigid shift of the average value of these levels by an amount given by delta E naught, which is negative. In addition to that, there will be a splitting, right? I'm now showing the splitting for a negative t. If t is negative, plus t will bring me down, minus t will bring me up. So the two solutions will be E naught, rigid shift for both, and then plus or minus t in the opposite direction. Now, in drawing this, I'm actually assuming that the absolute value of t is larger than the absolute value of delta E naught, which is not necessarily the case. I'm just assuming here that the absolute value of t is larger than the absolute value of delta E naught, but this is not necessarily the case. So I will have two states, this one and this one. Plus t was E plus, so this is E plus. Minus t is E minus. Okay. Oh, sorry, I removed the wave functions, but I'm sure you remember that E plus was phi 1 plus phi 2, and E minus was phi 1 minus phi 2, right? So if I now have to draw the wave functions on top of these energy levels, I'm going to get something like this. This plus this. The E plus state will have the two wave functions summed with the same sign, and E minus will be this wave function, and here minus the wave function. Okay? So phi 1 minus phi 2. This will be phi plus, and this will be phi minus. Okay. It's not over yet, because I have to now fill those states. How many electrons did I have at the beginning? 2 electrons, right? So where am I going to place those 2 electrons? I have to follow the hierarchy of energies, right? I have to place them in the lowest possible energy states. I have 2 electrons. Where do I place them? Spin up and spin down. I place them both in E plus. So in this picture, I'm going to place my 2 electrons both in this state, and no electron in E minus. Okay? This is a very important statement. And in fact, this is true as long as I work with H2. Suppose I was working with, say, H2 minus, the ion, the negatively charged ion. H2 minus would have 3 electrons. It would still, the potential would still be given by the 2 protons. So the whole exercise would be exactly the same. The only exception would be that now I would have to place 1 electron in E minus. Okay? Similarly, if I want to study H2 plus, the exercise would have been exactly the same, of course, if electron-electron interactions are negligible. If they're negligible, the exercise would be exactly the same, and I would have to fill this state with 1 electron only, with H2 plus, okay? Because I only have 1 electron available. But since, I mean, I'm talking about H2, let me assume that I'm filling this state with 2 electrons. Good. Yes?
Why not A minus?
Sorry, why not?
A minus to fill
I have 2 electrons, and I have 2 states out of my eigenvalue problems. I need to place the electrons in the lowest available state, right? So I have to place them here, both.
why A plus is the lowest?
Why E plus is the lowest? Because, well, this is true regardless of delta H. It's because of plus T and minus T. Right? These are the 2 energies. These are the 2 eigenenergies. With respect to E naught, which was the original state, I shift both of them by delta E naught, and I've done it through this middle green line. And then I have to, away from E naught plus delta E naught, go up or down by T, right? Notice that T is negative, so plus T goes down. Okay. Good. Yes?
Tell us, okay, like, could you give us some glimpse about the e-hoping and the on-state?
You give us some what? Sorry? Some.
Kind of, okay, glimpse for
You'll see it. I mean, we'll come back to this several times in the future. So you'll learn more about this delta naught and T in the future. Let me just solve this problem of the H2 molecule first, and then we'll look at more extensively at that. Okay, first consequence of this exercise. What can I say about the overall energy of my system? What was the original energy of the system where the 2 atoms were at infinitely far from one another? It was the 2 electrons in the 1s state, or E naught. Okay, so the original energy, if I'm talking about total energy of my system, at the beginning it was 2 E naught, right? If D is infinity, right? Twice the atomic energy. It's a negative number, of course. But if now we bring the 2 atoms close to one another, the electrons are no longer here. They're actually here. So it's actually twice E naught plus delta E naught plus T. And both of them are negative. So this energy here, sorry, the new one, is going to be below the original one. You have an energy gain of twice delta E naught plus T. Right? Let's put it in absolute value, right? If I'm talking about energy gain. It's like if I mean gain, I mean positive numbers, right? So I put an absolute value. So I've gained energy by doing that. I've gained energy by rewriting the wave functions, building these linear combinations of wave functions, and taking advantage of these 2 terms. That is, taking advantage of the fact that whenever this wave function sees the other Coulomb potential, sorry, here and here, there is a gain of energy in doing that. Takes advantage of the presence of the other nucleus. The physics is obvious, right? There is an electron on this side which sees the other nucleus and takes advantage of the other nucleus by building this linear combination. And similarly for the other one, takes advantage of the other nucleus by building this linear combination. Of course, you might actually argue that we are neglecting electron-electron interactions. So it is true that the electron takes advantage of the positive nucleus here, but in principle, it should also feel the repulsion of the other electron, which is on the other side. So our argument is not complete. One can, of course, show that the dominant effect is the nuclear one. It's the gain due to the nuclear interaction. And the electron-electron interaction is a correction to that. So I just want you to keep in mind that the gain is, there is also a loss mechanism in doing that which we're not considering because we are neglecting electron-electron interactions. But the argument is qualitatively the same, even if you include electron-electron correlations. So the first conclusion is that there is an energy gain, and the energy gain is proportional to the overlap of the wave function, to how much the wave function sees the other nucleus. By the way, you might actually argue that there is an inconsistency here in our discussion. And in fact, if I really want to be careful, I need to be a bit more precise about it. You remember we made this approximation. So we assumed that the overlap of the wave function on 1 and 2 was 0. Here we are retaining terms which have to do with the overlap of phi 1 and phi 2 here, or with phi 1 and the Coulomb potential on the other side. Okay? So we're not totally consistent when we do this. We are neglecting this and we are keeping this. Again, I'd like you to keep this in mind because all what we are doing goes through approximations which are just meant to make our calculations easy to do in a lecture. If I had to keep all these effects into account, I would take way longer than a lecture. But it is still true, trust me, that if you keep all these things properly into account, you will get something qualitatively similar to this one. But please keep in mind that there are a few inconsistencies in this. The other one was the one that you mentioned, namely, how can I build a charge in the middle if I'm assuming that this is 0, there's no overlap. Okay. Okay, first consequence, energy gain, net energy gain, if I form a bond. What do I mean by a bond? I mean, here I'm still playing with the original wave functions, right? So what do I mean that there is a formation of bond, that there is an accumulation of charge in the middle? After all, I'm still using the old wave function, so how can I get an accumulation of charge in the middle? That's not exactly true. Let's place ourselves at this point, exactly in the middle between the two atoms. And think about what the charge density was before and after we have introduced this linear combination. That is, suppose we look at the charge density at this point. If we just take the sum of the charge density coming from this atom and from this atom, or if we do it by constructing the charge density of the phi plus orbital. So, if I assume that the two atoms don't see each other, the density here would be the density of, would be phi 1 squared plus phi 2 squared, right? The density of electron 1 coming from atom 1, the density of electron 2 coming from atom 2 at this point. By symmetry, they are the same, right? Because we are at the same distance. And this is a very small number, by the way, because this is an exponential decay. So this will be the density that I would measure if atom 1 didn't know about atom 2 and vice versa. Let me now calculate the density which I obtain by assuming that this is the correct solution. Phi plus is what? I have to take phi plus squared, and I have to multiply times 2, because I have 2 electrons in that state. Here I have 1 electron here and 1 electron here. Now both electrons are in phi plus. And phi plus is 1 over square root 2, phi 1 plus phi 2. So this is 1 over 2, phi 1 plus phi 2 squared. But phi 1 and phi 2 at the center, they are equal. So this is actually 4 times phi squared, phi 1 or phi 2 squared. While this one, if phi 1 and phi 2 are the same, is just twice phi 1 squared. Right? Here I'm assuming that I'm at the center, and therefore phi 1 and phi 2 take the same value. Because by symmetry, right? The decay takes the same value here. So you see, just out of stupid mathematics, we get an additional factor of 2 here with respect to the original solution. So building a linear combination of the two states and filling only that one doubles doubles the value of the density at the midpoint. By the way, notice that if I had taken phi minus, at this point. Because phi minus is phi plus minus, sorry, phi 1 minus phi 2, phi 1 and phi 2 take the same value here, phi minus is 0 here. This is exactly the node of phi minus. Okay, so the charge density of phi minus here would be 0. So in other words, by building this linear combination of phi 1 plus phi 2 and phi minus plus phi 2, phi 1 minus phi 2, I've been able to shuffle the density at the center here and bring all the density here and zero the density in the phi minus state. The total density, if I sum phi plus and phi minus, of course, is the same because I've just been rearranging the same orbitals. But if I take one of them, the lowest one, then I gain a factor of 2 in the density. Okay? So the first conclusion is that energy goes down by an amount which is proportional to these overlaps. Second conclusion, the density at the center grows by, in this model, by a factor of 2 with respect to the original density, if assuming that the two atoms didn't see each other. So this is what, in this language, I mean in this model, corresponds to charge accumulation. There is indeed, with respect to the sum of the independent charges coming from the atoms, there is indeed a factor of 2 increase of the density at the center of the bond. That comes out from this model. Questions? Yes?
In the case that the two electrons are sitting in the phi minus,
Okay, so in the case that the two electrons are sitting here, yes?
do we have no concentration of electrons in the
Yeah, exactly. That you have no concentration of electrons. By the way, this is a physically realizable situation because while we know that delta E naught must be negative, T could be in principle positive. Okay? So if T is positive, of course, the state that lies below is E minus. And if T is larger than delta E naught, I mean, this becomes very low in energy. So what I need to fill is E minus. So it may be that at the center there is no charge density in the two cases. However, no, wait a sec. This is not entirely true. It is true if the two orbitals are the same. This statement holds if the two orbitals are the same. Unfortunately, in cases where T is positive, typically the two orbitals are not the same because they have to have opposite sign in order to make T negative, T positive. Okay? So I cannot do this, I cannot play this argument again. In fact, I suspect that I would probably find, regardless of the model, that there is still an increase in density at the center because they have opposite sign. So one would have to do the calculation, but I believe that what I just said before is wrong, namely, you always have an accumulation of charge because the fact that it's below means that the wave functions have an opposite sign, and therefore when I sum them with the opposite sign, I get a positive interference of the two wave functions. Yeah. Well, one would have to do the calculation, but I'm pretty sure that one would always get an accumulation of charge in the lowest state, regardless of the sign of T, because of the way the wave functions sum up. Yeah. Yes?
So this discussion only holds for electrons that are of the same kind of.
Yes, correct. This discussion only holds, at least most of the discussion only holds for electrons that belong to atoms of the same kind. We are not going to discuss what happens for, say, for example, molecules that are not composed of same atoms. You might easily, generalize these statements, right? You have, if the atoms are not the same, the two starting levels will be different. You will still consider a linear superposition of that sort. The difference here would be that E naught and E naught here would be different. There would also be some differences in delta E naught, so there will be, so the matrix will not be exactly A, A, B, B, but it will be A1, A2, B, B, BB for sure because it has to be Hermitian, so it must be symmetric. But A1 might be different from A2. And at that point, the two solutions are a bit more complicated. They're not just A plus or minus B, but they depend on the value of the difference between A1 and A2. And I mean, it's slightly different. The mathematics is slightly different, but the main conclusions would still hold, namely that by coming together, there will be a net gain of energy, which will be a more complex functions of these larger number of parameters because you have more parameters, and that there is an accumulation of charge in the middle. So the qualitative picture remains the same. It just gets a bit more complicated from the mathematical point of view. Yep. Any more questions? All right.